Hi friends, I am Professor Nadhamuni Reddy, Principal Armachar Institute of Technology and Sciences, Tirupati. So, in the ensuing session, this session, we will deal uh, with the sequencing model, another sequencing model, wherein n jobs will be there for processing through three missions. So earlier, first model was n jobs through two missions only. Now n jobs through three missions. So here we need to follow certain assumptions. So when n jobs are given, n means more than two, three or four, five, six, any number of jobs may be given. And there will be three missions, mission A, mission B, mission C. All these jobs in one particular order, they must go through first mission A. After processing the operation on mission A, each and every job should go to mission B, and after completing the operation on mission B, then only job will go through the mission C, go to mission C. So in the order ABC only, all the jobs must be processed through the machines. These jobs 1, 2, 3, 4, 5, and so on to n, the sequence of these jobs has to be found out. That is the problem here. So assumptions, all n jobs are required to pass through machines A, B, C in the order ABC only. We must not disturb this order. A, all the jobs should go through A for their first operation, for the first operation on them. Then the second operation will be on B on all the jobs. Third operation will be on mission C for all the jobs. So in this order only, jobs must be flown. So three missions processing data will be given. Processing data, processing time data for various jobs on three different missions will be given like this. So the same sequence of jobs over each mission has to be followed. Okay, whatever sequence that we find, the same sequence has to be found out. The objective is to find the optimal sequence of jobs which minimize the total elapsed time. So here also the objective of this model, sequencing model, is to find the total time of processing of all the jobs which minimizes the total elapsed time. What is the optimal sequence of jobs? And the optimal sequence, what is the total time required for completing all the jobs? So here Johnson's algorithm, the previous algorithm, Johnson's-Bellman algorithm, earlier we have discussed, that was which was applied to the n jobs two missions problem. Same algorithm can now be extended to solve this model also. To apply Johnson's algorithm, one of the following conditions is to be satisfied. So there are two conditions you must check it up. The smallest processing time on machine A. On machine A, processing times, operation times for all jobs on machine A, first list will be there. So identify the smallest processing time on machine A. That is in this list. If that smallest processing time is greater than the largest processing time on machine B, middle machine. So in the middle row, processing time data, identify the maximum processing time. So if the minimum processing time on the first list, machine A, is greater than or equal to the maximum or the largest processing time on machine B, that is the condition satisfied. One condition satisfied. If not, if that condition is not satisfied, then you can verify other condition also. Minimum processing time on machine C. On mission C, these are all the processing times, the operation times for various jobs. Identify the minimum here. If that minimum processing time on mission C is greater than or equal to the largest processing time on mission B, the middle mission, then also you can apply the algorithm. So you don't require to satisfy both the conditions. Either of this condition, first check the first condition. If it's satisfied, okay, you can leave it. You can what you call apply the algorithm. If the first condition is not satisfied, then only you need to check the second condition. If second condition also fails, then this algorithm cannot be applied. So if both conditions fail, you cannot apply Johnson's algorithm, then you can write the solution. Johnson's algorithm cannot be applied to this particular problem. That's enough. Both conditions fail. So naturally that situation may not arise once the data is given. So if any one of these conditions is satisfied, then as said earlier, Johnson's algorithm can now be applied. Now, Johnson's algorithm is applicable for n jobs 2 missions only, whereas here n jobs 3 missions. So we need to assume two imaginary missions or fictitious missions, call it as GI and HI. G and H. G and H are two fictitious missions or imaginary missions for which the processing times for these fictitious missions or imaginary missions are like this. GI equal to AI plus B. For the ith job, you must add the processing time on A and processing time on B. That sum of the processing times will be the processing time for that particular job, ith job on G. Similarly, if processing time on B and processing time on C is combined, summed up, that will become the processing time for H. So you must you must convert the given three machines problem into two machines problem by assuming two fictitious machines like this and converting the, the what you call the given problem into the n jobs two machines model first of all. Then you can apply the algorithm. When two machines data is only available, you can easily apply Johnson's algorithm as discussed earlier, the earlier model. You can find out the better sequence. Once best sequence is found out, then you can simply tabulate all the values to find out the total offset time, idle time on machine A, idle time on machine C, idle time on machine C. So these imaginary machines are assumed only to apply Johnson's algorithm. That's all. Johnson's algorithm can be applied only when any one of these conditions, condition A or condition B, is fulfilled. Any one of these two conditions must be fulfilled to apply the Johnson's algorithm. If you like to apply Johnson's algorithm, problem must be n jobs two machines model, whereas the given problem is this model is n jobs three machines. So n jobs three machines model will be converted to the n jobs two machines model like this. You must assume two fictitious machines where G is the combination of A and B, H is the combination of B and C. That's all. So we will demonstrate with the help of an example like this. See here, by looking at this table, you can very easily understand that there are five jobs, 5 jobs given. For each and every job, processing times, operation time on machine A given in the first list, operation time on machine B is given in terms of minutes or hours, whatever it is. In terms of on machine C, these are the processing times on machine C. So like this data is given. Just verify the condition whether first of all this can be what you call Johnson's algorithm can be applied to solve this model. First of all, identify the minimum processing time on the first list. Minimum processing time on the first list 4, 9, 8, 6, 5. Minimum is 4. Minimum processing time on A is 4. Then maximum processing time on B 5, 6, 2, 3, 4. Maximum is 6. So maximum processing time is this. So minimum processing time on A must be greater than or equal to maximum processing time on B. Is it true? No. That condition failed. So go for second condition. If first condition is failed, go for second condition. What is second condition? The minimum processing time on the last machine. Minimum processing time on the last machine is 6. Maximum processing time on machine B is 6. So minimum processing time on machine C is greater than or equal to maximum processing time on greater than or equal to. So 6 greater than or equal to 6. That is satisfied. First condition failed, second condition satisfied. Hence you can go for Johnson's algorithm. You can apply Johnson's algorithm. So when you would like to apply Johnson's algorithm, first of all, this data, three machines data must be converted to two machines data. How? So assume jobs, there are five jobs, 1, 2, 3, 4, 5 jobs. Assume G, machine H. For machine G, what is the time? AI plus BI. GI, processing time for GI for the ith job equal to AI plus BI. So processing time for H equal to, for the ith job equal to HI equal to BI plus CI. So how will you get? For GI, 4 plus 5 for this. For second job, 3 plus 9 plus 6. For third job, 8 plus 2. For fourth job, 6 plus 3. For fifth job, 5 plus 4. These are the processing times for G. See, 9, 15, 10, 9. So first two rows added, this becomes, when you add first two rows, this becomes the processing times for G. When you add last two rows, this row and this row, processing times on machine B, processing times on machine C. 5 plus 8, 13, 6 plus 10, 16, see, 13, 16, like that. So now there are only two machines, G and H. There are jobs, 5 jobs. So now the problem contains 5 jobs on two machines. So this data is enough to find out the best sequence of jobs. So this data is used, this table data is used only to find the sequence, remember. So 5 jobs and 5 compartments must be mentioned here. 5 compartments must be mentioned. So identify which is minimum here. So there are too many ties it seems. 9, 9, 9. 9 and 8, 10, 15, 8. 8 is minimum. In all the processing times, minimum is 8. This corresponds to the job 3. So 8 is occurring on the second machine, not on the first machine. Hence, this corresponding job number must be positioned at the end. End అంటే ఇక్కడ వస్తుంది 3. So any assume that these are all the empty compartments. First 3 must be placed here. Last compartment is filled. So once this is over, this must be removed. This data must be removed. Removed in the sense temporarily don't consider this column. Then the remaining columns 9, 15, 9, 9, 13, 16, 10, 15. So 9, 9, 9. So tie exists in the first emission itself. So either you follow this one first, then this one, this one. 1, 4, 5. 1, 4, 5. 9, 9, 9. All these are minimum compared to all the other values. This is occurring on the first emission only. So first corresponding job number 1 must be placed here. And remaining jobs, remaining, and I mean with the same minimum processing time 4 or 5. 1, 4, 5 can be placed. Instead of 1, if we assume this is also same value, same minimum value. Instead of 1, if you assume this first, this corresponds to the job number 4. This is also appearing on the first emission itself. Hence 4 comes first. This is another alternative sequence, alternative best sequence. 4, 4 is given here. 1 you can put, 5 you can put. So 1, 4, 5 can be used. 4, 1, 5 can be used. Or 5, 1, 4 can be used. Or 1, 5, 4 can be used. Or 1, 4, 5 can be used. See, these are all the different ways you can put. All these are best sequences only. All these are supposed to be best sequences. And only remaining job is only 2. That must empty compartment is this one. Here you can put 2. So that way, so first this position is fixed. Why? Because this 8 corresponds to 8 is the minimum processing time of all, corresponds to 3. Third job is placed at the end since it is occurring on minimum processing is occurring on second machine. Then 9, 9, 9. If you omit this third column, this column if you omit, the remaining columns, see 9, 15, 9, 9, 13, 16, 10, 15. So of all these 9 is the minimum processing time. Tie occurs for the first job, tie occurs for the first job, fourth job, and fifth job. Anyone can be placed in the beginning. Next one follows, next one follows. Of these jobs, 1, 4, 5. So 1, 4, 5 is one way you can write. 4, 1, 5 another alternative. 5, 1, 4 another alternative. 1, 5, 5, 1, 4. 1, 5, 4 another alternative. 1, 4, 5 another alternative. So like that, different ways you can write. And only remaining empty box is this one. 2. Second job is left remaining. So this way, you can find the various optimal sequences. Any sequence you follow, either this optimal sequence or this optimal sequence or this optimal sequence or this sequence. Any optimal sequence you can follow. You don't require to compute for all the optimal sequences. All these are optimal sequences only. All these sequences are optimal sequence only. This one or this one or this one, this one, this one. One sequence you can follow, and the total offset time will be same. In all the other sequence also you can test it, or you can what you call tabulate and find out. So in the examination, you choose only one sequence, either of these sequences. One best sequence is enough. To 1, 4, 5, 2, 3. This last sequence has followed 1, 4, 5, 2, 3. Anyone instead of this one, any sequence you can follow. All these are optimal sequences only. So 1, 4, 5, 2, 3. So optimal sequence is written. Now when you are writing time in, time out for the machines, at what time job enters a particular machine, at what time job comes out of the particular machine. These machines, machine A, machine B, machine C should be used, not the fictitious machines G and H. This data is used to find only the sequence, remember. N jobs 3 machines model is converted to N jobs 2 machines model only to determine the best sequence. Here different alternative best sequence have come. Okay, it's a different matter. So this particular data is used only to find the best sequence. Once best sequence is found out, if alternatives are there, any one sequence you can follow. Any one sequence you can follow. So hence here the last sequence is followed. Optimal sequence. So for the once optimal sequence is written in this table, you should consider the processing times on the original machines. Machine A, machine B, machine C. G and H are only fictitious missions or imagined missions. The data was used only to find the best sequences, that's all. Once the best sequence is found out, time in, time out must be computed on the real machines. Machine A, machine B, machine. Originally, we are given three machines: machine A, machine B, machine C. Hence, the table contains this one: machine A. What time it comes in? So at clock time 0, the first job enters. So first job enters at clock time 0. What is the operation time for the first job on machine A? 4. First job on machine A 4. So clock time 0 start అయింది. 0 plus 0 plus 4, 4. At clock time 4, it comes out. Okay. At clock time 4, it can take next job in the sequence. Fourth job వస్తుంది. At clock time 4, it starts. So fourth job ki what is the time on first machine? 6 minutes. So 6 minutes. So at clock time 4, it starts. 4 plus 6, 10. Then at clock time 10, it can take next job in the sequence. What is the operation time for the fifth job on the first machine? Fifth job on the first machine, 5 minutes. 5 minutes. So 10, clock time started 10, clock time at what time it ends? 10 plus 5, 15 minutes. That is, next job will be taken exactly at clock time 15. So like that. So plus operation time if we take 24. So next job will be taken exactly at clock time 24. 24 plus operation time for the third job on the first machine, if you sum up, that becomes 32. So these are the times, clock times at which these jobs comes out one after one from machine A. So first job enters at clock time 0, comes out at clock time 4. Fourth job comes out, loaded at clock time 4 and ended its operation on machine A at clock time 10. Next fifth job loaded exactly at 10, clock time 10, comes out at clock time 15. So that way, at what time the jobs entered, what time jobs came out after after the operation is over on machine. This is given here. So this table must be completed first of all. Then you write machine B. So I told you earlier, operation on the first machine must be completed. Then only any job will come onto the machine B. So the first job in the sequence is initial job was first. That was busy on the first machine. That was getting operated on the first machine up to clock time 4. Clock time 4 it was released. So at clock time 4 it will go to the machine B. Move time is negligible. అక్కడి నుంచి ఇక్కడ రావడం move time negligible. So at clock time 4 operation starts for job 1 on machine B. So what is the operation time for the first job on machine B? That must be added to find out at what time it comes out. So 4 plus first job machine B 5. 5 minutes operation time 5 minutes. So 4 plus 5. Here you can write 4 plus 5 9. So ఇక్కడ 9, ఇక్కడ 10. See, this machine has completed the operation on this particular job at clock time 9. Whereas the next job, that is fourth job, was held up in the previous machine itself up to clock time 10. So it is ready for loading onto the next machine only at clock time 10, not at clock time 9. Remember, up to clock time 10 it was busy in the previous machine itself. This will come on to the machine B, can be loaded only at clock time 10. So plus what is the operation time for the fourth job on machine B? Fourth job on machine B. Fourth job on machine B. 3 minutes only. 3 minutes only. 3 minutes. So 10 plus 3. Clock time 10 started. Plus 3 minutes. At clock time 13 it comes out. So clock time 13. Up to clock time 13 it was doing work. Machine B was doing work on fourth job. What about this? This next job in the sequence was held up in the first machine itself up to 15. Clock time 15. Hence, this job cannot be loaded onto the machine at clock time 13. It can be loaded only at clock time 15. Why? Because it has to come out. It has to come out of machine A, then only it can be loaded. So at clock time 15 it can be loaded. So for the fifth job on machine B, what is the operation time? Fifth job for 4 minutes. 4 minutes. For the fifth job, 15 plus 4. Night clock time 19 it comes out. Here 19, here it is 24. So by clock time 19, the job on the fifth job operation was over on machine B. It is ready for taking, but the next job, that is 2, was held up in this mission up to clock time 24. Hence, this can be loaded into the mission up to clock time 24. 24. So 24 plus operation time on the second job. Operation time on the second job on the mission B 6. 6. See, 24 clock time started. 24 plus 6 30. So here 30, here 32. So only at clock time 32 it can load, third job can be loaded onto mission B. So 32 plus operation time on this. Operation time, something wrong here. Operation time on third job. Operation time on third job on mission B 2 minutes. Okay. So 32 plus 2, 34. So these are the times, clock times at which each job has come out. First job has come out of mission B at 9. Fourth job came out at clock time 13. Fifth job came out of mission B 19. Second job came out at 30. Third job came out of 34. So this way they came out. Now mission C is also there. So at what time mission C can take up the first job in the sequence? Only after it has completed the operation on mission A first, then on mission B, then and then only the job 1 can be loaded onto this. So at clock time 9. At clock time 9, it has completed its operation on mission B. So at 9 only it can take the next job in the sequence. I mean the job can be loaded onto mission C 9. So for first job, what is the operation time on mission C? That must be added to get the this one. First job 8 minutes. 8. So 9 plus 8, 17. So at 17, up to 17 minutes, clock time 17, it was busy. Whereas next job is ready by 13, clock time 13. But this machine was busy doing this operation on the first job up to clock time 17. So though this job is ready by 13, clock time 13, the machine is busy up to clock time 17. Hence, at clock time 17 only the operation for the fourth job can be started. That is, fourth job can be loaded. So fourth job machine C operation time, fourth job machine C 7 minutes. That must be added to get the completion time. 7, 17 plus 7, 24. So here 24, here 19. So next job came out at clock time 19, whereas the machine is busy up to clock time 24. Hence only at clock time 24 it can start the work on machine 5. Sorry, job 5. So job 5, clock time started at clock time 24 plus operation time on this. See, fifth job, 11, the job 11. So 24 plus 11, 35. Here is 35, whereas next job came out after machine B at clock time 30 itself. Machine was busy on this job to clock time 35. So it can take this job in the sequence only at 35, clock time 35. Plus operation time that becomes 45. This time came out. Then 45, this is 34. See, so machine was busy up to clock time 45 on job 2. So next job in the sequence is 3. That must be taken for loading onto machine C only at a clock time 45, not at this time 34. So clock time 45 plus operation time 6 minutes, so 51. So total time required for completing the operations on all the jobs will be equal to 51 minutes. This is how total elapsed time is computed. Then in the 0 to at clock time 0, operation started on the first initial job, and the last job in the sequence, the sequence is third job that has completed the operation on C, the last mission itself, by clock time 51. So total time is 51 minutes. In the span of 0 to 51 minutes, how much time machine A was idle? So 0 to 4 busy, 4 to 10 busy, 10 to 15 busy, 15 to 24 busy, 24 to 32 busy. There afterwards machine A was idle. After 32 machine A was idle. So from 32, from clock time 32, clock time 51, machine A was idle. At 51 minus 32, that is idle time. Idle time on machine is 51 minus 32. So in this total span of 0 to 51 minutes, how much time machine A was busy? Up to clock time 32 only. From clock time 0 to clock time 32, no single minute it has wasted. It was completely busy up to clock time 32. There afterwards it was idle. So idle time equal to 51 minus 32. Then idle time on machine B. See, so in the beginning, first 4 minutes, it did not start the operation. machine B. First 4 minutes in the span of 0 to 51, for first 4 minutes it was idle. Then here, operation completed by 9, next job was taken at 10. Here 1 minute. Then at 13, at 15. Operation completed at 13, here it is 15. It started the operation 15. And 2 minutes idle, machine was idle. Then 19, 24. 19, 25, 5 minutes it was idle. And 30, 32, here 2 minutes was idle. Then thereafter 34, after 34 clock time 34 also it was idle. So you must sum up all these values. Here 4, then here 10 minus 9, 1, 15 minus 3, 2, 24 minus 19, 5, 32 minus 30, 2, plus from 34 minutes clock time 34 to clock time 51. So machine B was busy only up to, was doing the work only up to clock time 34. Thereafter it was idle up to 51. So 51 minus 34. So if sum up all these idle times, that comes to be 20 hours. Sir, 20 minutes, sir. If you so time units say whether it is hours or minutes depending upon. So time units and 20 time minutes it was idle. Then coming to machine C, if you see, machine C started at clock time 9. So first 9 minutes it was idle. 9 to 17 working, 17 to 24 working, 24 to 35 working, 35 to 45 working, 45 to 51. There are no idle times here. Operation started at clock time 9. Only that is only the idle time for it. From clock time 9 to clock time 51, it was totally busy. So idle time on machine is equal to 9 hours. This is how you have to do the problem here. So remember, once again I tell you, so n jobs 3 machines model can be solved by extending the Johnson's algorithm. Johnson's algorithm can be extended. And there are two conditions to be met. There are two conditions, these two conditions. Smallest processing time on the first machine list greater than or equal to largest processing time on the second machine list, machine B. This condition is satisfied, that's enough. You can go for applying Johnson's algorithm. If this condition fails, next condition you will check. Smallest processing time on third machine greater than or equal to largest processing time on machine B. If this condition is fulfilled, then also you can apply Johnson's algorithm. If both conditions fail, then you can simply write Johnson's algorithm cannot be applied. We cannot solve the problem using Johnson's algorithm. So here, in the first condition, in this particular example case, first condition failed, second condition true, second condition is okay, satisfied. Hence, Johnson's algorithm can be applied. Any one condition is enough. So, Johnson's algorithm is applicable for n jobs 2 machines model. Hence, n jobs 3 machines model must be converted to 3 machines model should be converted to n jobs 2 machines model by assuming two 50cc machines G and H. So, for these two 50cc machines, processing times will be computed like this. Processing time on machine A, processing time on machine B for a particular job. If you sum up, that will be processing time on G, like that. So GI equal to AI plus BI, HI equal to AI, BI plus A. So like that, you will get this 50cc machine processing time data. So now the problem is converted to 2 machine data, n jobs 2 machines, 5 jobs 2 machines. So you can employ the algorithm, simply algorithm, different alternative sequences, best sequences will be there. All these are best sequences only. Any sequence you can follow, or all the sequences you can just verify. Any sequence you follow, the total elapsed time will be 51 minutes only. Instead of this sequence, you take another alternative sequence. This optimal sequence if you choose, then also it will be 51 minutes. Idle times may be different, that's all. So any one optimal sequence, complete these computations to calculate total elapsed time. That is enough. Okay, this is how Johnson's algorithm is applied to n jobs 3 machines data. So here the optimal sequence is to be determined basing on the fictitious machine data. That fictitious machine data is only used to determine the sequence. Once sequence is determined, then time in time out for to be calculated for the real machines, machine A, machine B, machine C, not on the fictitious machines. Remember. So total elapsed time should be found out. Idle times on machine A, idle times on machine B, idle times on machine C must be computed. Okay. Right.